Hello there and welcome to section 12.9 on curvature. In this intro video we're going to begin our discussion of curvature, but before we start that I want to recall something that we saw briefly back in section 12.5 known as the unit tangent vector to a curve. And I have the definition here. It says, let the curve C be described by the vector function r of t if C is a smooth curve, meaning that the velocity vector v is non-zero for all t. Then the unit tangent vector to C is this vector, capital T, which by definition is the velocity vector divided by its magnitude. Okay, so a couple comments here. The first is, why do we require the curve C to be a smooth curve, which again means that the velocity vector is non-zero for all t? Well, you see in the definition of the unit tangent vector that we're dividing by the magnitude of the velocity vector. So if the velocity vector were to equal 0 at some particular time, then we're going to run into an issue in defining the unit tangent vector at that time. Okay, so as long as the velocity vector is well defined and is non-zero, we can define the unit tangent vector. All right, next I want to highlight the fact that the unit tangent vector, by its very construction, is the unit vector that points in the direction of the velocity vector v. Okay, so since we are taking the velocity vector and dividing it by its magnitude, that implies that the magnitude of the unit tangent vector is 1 for all t. And since the unit tangent vector is really a positive scalar multiple of the velocity vector, we're just scaling it by 1 over the magnitude of the velocity vector, that implies that the unit tangent vector points in the same direction as the velocity vector. Okay, now we know that the velocity vector points in the direction tangential to our path in the direction of increasing time. So put another way, if we were to drive along this path in the direction indicated by these red arrows, then the velocity vector will always point in the direction of our headlights. And since the unit tangent vector points in the same direction as our velocity, that implies that this vector t is also tangential to our path. And so the name unit tangent vector, right, is very appropriate because, again, capital T is a unit vector that points tangential to our path. All right, cool. So I then note that while the magnitude of the unit tangent vector does not change, right, it has magnitude 1 for all t, its direction certainly can change as we move along our path. And the rate at which the direction of the unit tangent vector changes as we move along our curve, that tells us the rate at which the curve turns. And it's this rate of turning that's known as curvature. Okay, so with that in mind, let's consider the following example. So I have these two paths, and I want to compare the curvatures of these two paths. And as you might suspect, the curvature of the path on the left is greater than the curvature of the path on the right. Okay, so put another way, if we're going to move along this path on the left, our direction is going to have to change at a much greater rate in order to stay on this path than what we're going to see over here on the right. To stay on the path on the right, we don't have to change our direction very much. Okay, so now to fill that out with some more details, we're going to measure everything relative to arc length s. Okay, so we're going to choose some base point on our path, and there we'll take arc length just to equal 0. And let's say I walk s units along our yellow path from our base point, and I wind up right here. And here I've just indicated our unit tangent vector at that particular location. All right, now I want to know the rate at which our unit tangent vector changes with respect to arc length. Okay, so to measure that, I'm going to walk a little bit further along our path, and I'll call that incremental change in arc length, delta s, and I'm going to measure the unit tangent vector at this nearby point. Okay, and if I want to know the rate of change of the unit tangent vector with respect to arc length, I then want to look at the change in the unit tangent vector. Okay, so I'm just going to translate these unit tangent vectors so their tails coincide, and then the change in the unit tangent vector, that's this vector in orange that runs from tip to tip. All right, now notice if we do the same thing for the path on the right, the change in the unit tangent vector is considerably less than what we see on the left. And so for that reason, okay, this will give rise to a larger curvature for the path on the left than what we see on the right. Okay, so we're going to make the following definition. Okay, we're going to define the curvature, which is indicated by the Greek letter kappa at a point, to be the following scalar function. Okay, we're going to define it to be the magnitude of the derivative of the unit tangent vector with respect to arc length. Okay, so keep in mind that when we differentiate a vector function, we get another vector function, and you see here by definition the curvature is the magnitude of that corresponding vector function. So that in turn gives us a scalar function. Okay, and this derivative, right, dt ds, what is it really measuring again? Well, it's really what we're doing up here. It's measuring the rate of change in our unit tangent vector with respect to arc length. Okay, and we're calling the curvature just the magnitude of that rate of change. Okay, so now let's go ahead and talk about how we can compute curvature. Okay, so the definition in terms of arc length turns out to be not a terribly computationally friendly way to go about finding curvature. But we can compute curvature in terms of the parameter t as follows. We can use the chain rule. Okay, so the unit tangent vector depends on arc length, which again is just telling us the distance we've covered along our path from some reference point. And that distance s, right, arc length s, that depends in turn on time, t. Okay, so I can consider these intermediate rates of change, so dt ds and ds dt, and the chain rule says that this rate of change, dt d little t, that's equal to the product of these intermediate rates. And now if I divide both sides of this equation by ds dt, I find that the derivative dt ds is this ratio of derivatives. And now if I want to measure the curvature, I want the magnitude of this derivative dt ds. And so on the right, well, I'm going to be taking the magnitude of this derivative dt d little t, and notice here, right, when you differentiate the vector function capital T, you get in turn another vector function. So it makes sense to take the magnitude of that derivative in the numerator. Now in the denominator, s, arc length, is a scalar. And so this derivative ds dt is a scalar quantity. So note here I have an absolute value in the denominator. Okay, now what is this derivative ds dt? Well, it's the rate of change of our distance covered along our path with respect to time. Well, that sounds a heck of a lot like speed, and in fact, that's exactly what it is. Okay, so let's say I have my path here, and I have my reference point where arc length s is taken to be 0, and we'll start our timer at this reference point, so t is 0 as well. And now at a later time, well, I've moved a certain distance along our path, and that distance is what we're calling s of t. Okay, now we know from section 12.8 to measure this arc length, we want to integrate our speed function with respect to time. Now notice here I'm using t as the upper bound of integration, so I don't want to use t for my variable of integration here, so I'm just using the letter u there just to distinguish the letter of integration from the bound. Okay, but in any event, right, if I want to find the rate of change of the arc length s with respect to time, I'm going to compute the derivative of this integral. And we know from the fundamental theorem of calculus version 1 that that gives us just the integrand evaluated at the upper bound of integration here. And so in other words, right, we recognize this as the speed of our particle that's moving along our path. So in conclusion, right, we say that the curvature by definition is the magnitude of this derivative dt ds, which in turn is equal to this quantity. It's the magnitude of the derivative of the unit tangent vector with respect to time divided by the speed of our particle. And the nice thing about this last expression is that it allows us to compute the curvature in terms of the parameter t as opposed to arc length s. And in the next video, we will illustrate how that works. Thanks so much.